Black holes are some of the most fascinating and mysterious objects in the universe. They have been the subject of scientific study and speculation for decades, and yet, we are still learning new things about them. Today, we're going to share with you 10 facts about black holes that you probably didn't know. Contrary to their name, black holes are not holes or empty spaces. Instead, they are incredibly dense objects with such strong gravitational forces that nothing, not even light, can escape their pull. This means that any matter or energy that comes too close to a black hole will be pulled in and become part of the black hole's mass. One way to think of a black hole is as a point in space with almost infinite density. The mass of a black hole is concentrated in a small region called the singularity, where the laws of physics as we know them break down. The gravitational pull of a black hole is so strong that it can distort space-time, the fabric of the universe, causing objects to bend and warp as they move near the black hole. This effect is known as gravitational lensing and has been observed in images of distant galaxies. Despite their ominous reputation, black holes play a crucial role in shaping the universe as we know it. They are responsible for the formation and evolution of galaxies, and their extreme conditions provide a unique laboratory for testing the limits of our understanding of physics. One common misconception about black holes is that they are all the same size, but this is not true. Black holes can actually range in size from just a few times the mass of the Sun to billions of times the mass of the Sun. Scientists categorize black holes into 3 different sizes: small, intermediate, and supermassive. Small black holes are thought to form when a single massive star collapses under its own gravity at the end of its life. These black holes can be just a few times the mass of the Sun and are relatively rare. Intermediate black holes are more mysterious, as scientists are still not sure how they form. These black holes range in size from 100 to 100,000 times the mass of the Sun. Finally, supermassive black holes are the largest of the 3 and can be billions of times the mass of the Sun. These black holes are typically found at the centers of galaxies and are thought to form through the merging of smaller black holes and the accretion of gas and other material. The size of a black hole is determined by its mass and the amount of material it has swallowed up. As more matter falls into a black hole, it gains mass and becomes more massive. However, the size of the event horizon, or the point of no return, also grows larger as the black hole gains mass. Therefore, the larger the black hole, the stronger its gravitational pull and the larger its event horizon. The size and strength of a black hole's gravitational pull can also have a significant impact on the surrounding environment, such as distorting light or even affecting the orbits of nearby stars. One of the most intriguing facts about black holes is that they have a massive gravitational pull. This gravitational pull is so strong that it can distort space-time, causing time to slow down. As you get closer to a black hole, time appears to slow down compared to someone who is further away from it. This phenomenon is known as time dilation, and it was first predicted by Albert Einstein's theory of relativity. According to this theory, gravity is not a force, but rather a curvature of space-time caused by the presence of mass or energy. The closer you are to a massive object like a black hole, the more it warps space-time, causing time to slow down. For example, if you were to orbit a black hole at a distance of 1,000 kilometers, time would appear to be moving slower for you than for someone on Earth. The difference would be small, but it would still be noticeable. If you were to get closer to the black hole, time would slow down even more. At a distance of 500 kilometers, time would slow down by about 20%. This effect has been observed in experiments on Earth using atomic clocks. Scientists have found that the closer a clock is to Earth's surface, the slower it runs due to the planet's gravitational pull. Similarly, the closer a clock is to a black hole, the slower it runs due to the black hole's gravitational pull. The time dilation effect near black holes has some interesting consequences. For example, if you were to travel close to a black hole and then return to Earth, you would have aged less than someone who stayed on Earth the whole time. This means that time travel to the future is theoretically possible by traveling close to a black hole and then returning to Earth. Black holes are massive objects that have a tremendous gravitational pull. According to Einstein's theory of general relativity, this gravitational pull can warp the fabric of spacetime around the black hole. This means that anything that gets close to a black hole will be affected by the distortion of spacetime. One of the most fascinating consequences of this effect is known as gravitational lensing. Gravitational lensing occurs when the gravitational pull of a black hole bends the light that passes near it, causing it to curve and distort. This can lead to the creation of optical illusions, such as multiple images of the same object or the magnification of distant objects. Another consequence of the warping of spacetime is that time itself can be affected. Near a black hole, time slows down significantly due to the strong gravitational field. This means that someone who is close to a black hole will experience time at a slower rate than someone who is further away. Additionally, the warping of spacetime can also create a phenomenon known as time dilation. Time dilation occurs when time passes more slowly in a strong gravitational field, which means that someone near a black hole would age more slowly than someone who is further away. This effect has been observed and measured using precision atomic clocks on Earth and in orbit around the Earth. In summary, black holes are not just objects that suck matter into them. They also have a profound effect on the fabric of spacetime, warping it in ways that can cause optical illusions and distortions of time itself. The study of black holes continues to be a fascinating and important area of research in the field of astrophysics. Black holes are not static objects, and they can actually merge with each other. When two black holes are in close proximity to each other, they start to spiral inwards due to the force of gravity, emitting gravitational waves. As they get closer and closer, they eventually merge into a single black hole, releasing a massive amount of energy in the form of gravitational waves. The first detection of gravitational waves from the merger of two black holes was made in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. Since then, multiple mergers have been detected, including the largest and most massive black hole merger ever observed in 2020. Merging black holes can have significant effects on the surrounding space and objects. For example, the merger of two black holes can create a burst of energy that can be detected by telescopes on Earth. It can also cause the ejection of matter and radiation, known as a jet, which can impact other objects in the vicinity. Furthermore, black hole mergers can have a significant impact on the study of astrophysics and cosmology. By observing the gravitational waves emitted by the merger, scientists can learn more about the properties of black holes, including their mass, spin, and location. This information can help in understanding the formation and evolution of black holes, as well as the larger-scale structure of the universe. Contrary to popular belief, black holes are not immortal. They do, in fact, have a lifespan. However, it is an incredibly long one, lasting trillions of years. Black holes lose mass through a process called Hawking radiation, which was first predicted by physicist Stephen Hawking in 1974. Hawking radiation is the result of quantum effects near the event horizon, the point of no return around a black hole where the gravitational pull becomes so strong that not even light can escape. As black holes lose mass through Hawking radiation, their temperature increases, causing them to radiate even more energy. This process continues until the black hole eventually evaporates away completely. For a black hole with the mass of the Sun, this process would take about 10 to the power of 67 years, an incredibly long time even by astronomical standards. However, there is a catch. The larger the black hole, the longer it takes to evaporate. Supermassive black holes, which can have billions of times the mass of the Sun, would take much longer to evaporate than smaller black holes. In fact, they may take so long that they could be considered immortal on human timescales. Despite their long lifespan, black holes will eventually cease to exist, making them one of the few things in the universe that is not eternal. One common misconception about black holes is that they are the same as wormholes. While both involve extreme distortions of space-time, they are very different phenomena. A black hole is a region of space-time where the gravitational pull is so strong that nothing, not even light, can escape from it. The boundary around a black hole is called the event horizon, and once something crosses it, it is inevitably drawn towards the singularity at the center of the black hole. On the other hand, a wormhole is a hypothetical tunnel-like structure in space-time that connects two separate points in the universe. In other words, a wormhole is a shortcut through space-time that could potentially allow for faster-than-light travel. While black holes and wormholes are both fascinating concepts, they have very different properties and implications for our understanding of the universe. Wormholes are purely hypothetical at this point and have not been observed, while black holes are well studied and have been observed directly or indirectly through their effects on nearby matter. Additionally, black holes are not a means of transportation or travel. While a wormhole could potentially allow for faster-than-light travel, the extreme gravitational forces around a black hole would make it impossible to navigate or survive close to it. In conclusion, black holes and wormholes are both fascinating phenomena that play important roles in our understanding of the universe. However, they are very different from each other, and it is important to understand their distinctions and properties to fully appreciate their significance. Despite the name, black holes are not necessarily black. In fact, some black holes emit radiation, making them visible to telescopes. This phenomenon is known as Hawking radiation, named after physicist Stephen Hawking, who proposed its existence in 1974. According to the theory of general relativity, black holes are formed by the collapse of massive stars. As the star collapses, its gravity becomes so strong that it traps all the light and matter inside it, forming a singularity, a point of infinite density and zero volume. However, due to quantum mechanics, it is possible for black holes to emit particles and radiation through a process known as quantum tunneling. This radiation is not actually coming from inside the black hole, but rather from its event horizon, which is the point of no return beyond which nothing can escape the black hole's gravitational pull. As particles and antiparticles are created in pairs in the vacuum of space, sometimes one particle falls into the black hole while the other escapes. The escaping particle carries away energy, causing the black hole to lose mass and eventually evaporate. This process is extremely slow for larger black holes, taking trillions of years for a black hole the mass of our Sun to evaporate, but could happen much faster for smaller black holes. In 2020, astronomers detected a burst of energy coming from a black hole in the Ophiuchus galaxy cluster, which they believe to be the result of Hawking radiation. This discovery not only confirmed the existence of Hawking radiation but also suggested that there could be many more black holes emitting radiation throughout the universe. So, while black holes are known for their blackness, some of them can actually emit radiation and be visible to us, thanks to the phenomenon of Hawking radiation. Despite their name, black holes can actually be detected indirectly by observing their effects on nearby matter. For example, when a star gets too close to a black hole, the intense gravity can cause the star to be torn apart in a process called spaghettification. As the star's material is pulled into the black hole, it heats up and emits X-rays that can be detected by telescopes. Another way that black holes can be detected indirectly is through the gravitational waves they produce. When two black holes merge, they create ripples in spacetime that can be detected by gravitational wave observatories like LIGO and Virgo. Astronomers can also look for the effects of black holes on nearby stars and gas. For example, if a black hole is orbiting a star, it can cause the star to wobble back and forth in a detectable way. The accretion disk of matter around a black hole can also emit bright radiation in the form of X-rays and gamma rays, which can be detected by telescopes. Overall, while black holes themselves cannot be directly observed due to their light-trapping nature, their effects on surrounding matter and spacetime provide clues to their existence and properties. One of the most fascinating and mysterious aspects of black holes is their potential role in helping us understand the universe as a whole. For one, studying black holes can shed light on some of the most fundamental principles of physics, such as the relationship between matter and energy. Additionally, black holes could hold the key to understanding the nature of dark matter, which makes up roughly 85% of the matter in the universe, but is invisible and has never been directly observed. Another reason black holes are of great interest to scientists is their potential to help us better understand the origins of the universe. By studying black holes and the radiation emitted by them, known as Hawking radiation, scientists may be able to glean insights into the earliest moments of the universe and the conditions that led to the Big Bang. Black holes may also play a role in helping us understand the structure and evolution of galaxies. Some scientists believe that the supermassive black holes found at the centers of galaxies play a crucial role in shaping the structures of these galaxies over time. Furthermore, black holes have been studied as potential sources of energy. By harnessing the energy emitted by a black hole, scientists could theoretically generate vast amounts of power. In conclusion, the study of black holes has the potential to unlock some of the most profound secrets of the universe, from the nature of dark matter to the origins of the cosmos itself. It is a field of study that continues to captivate and intrigue scientists and lay people alike. I hope you've enjoyed learning about these fascinating objects. Thanks for watching, and be sure to subscribe for more amazing videos.